Welcome to the Explainer. Today we're going to decode the mathematical language that describes, well, just about everything that moves or changes, from a simple falling apple all the way to the orbits of entire galaxies. Yep, we are talking about differential equations. Okay, let's start with a really big idea. We're all used to equations that solve for a static number, right? Like x equals 5. But what if you could write an equation for a process, not just for a single moment in time, but for the rate of change itself? Like how fast a population is growing or the speed at which your coffee cools down.
And that is exactly what a differential equation is. It's an equation that links a function to its own rates of change, its derivatives. You can think of it as the literal mathematical language we use to describe how things change over time.
To really get a handle on this, let's try not to think of it as just a bunch of math problems. Let's think of it as learning a powerful new language, a language that tells the story of how things evolve.
Here's a great way to picture it. A simple equation, something like y equals x squared. That gives you the position of a point. It's a snapshot. But a differential equation? That gives you the whole movie. It doesn't just tell you where something is. It tells you its velocity, its acceleration, the entire path it's taking. It's the full story.
And just like any language, this one has its own grammar. So to really understand it, we've got to start with two fundamental terms that help us classify every single equation we come across: order and degree.
So the order is pretty straightforward. It's just the highest derivative you see in the equation. A first-order equation is talking about a rate of change, like velocity. A second-order one is talking about the rate of change of the rate of change, like acceleration. And the degree? Well, that's just the power that highest-order derivative is raised to. These two things are like the basic stats for any differential equation.
Now, here's a really crucial little detail about the degree. It's only defined if the equation is a nice, simple polynomial of its derivatives. If you ever see a derivative kind of trapped inside another function, like the sine of dy dx, we just say the degree is undefined. It's a small rule, but a really important one for classification.
All right, so now that we have the basic grammar down, we can start to identify the different, well, you could call them species of these equations. And just like in biology, classifying them is the first step to understanding how they behave and, more importantly, how to deal with them. Think of these classifications as your roadmap. An equation is linear if the variable and its derivatives are all just to the power of 1. Nice and simple, no y squareds or tricky stuff. It becomes nonlinear the moment it breaks that rule. And it's homogeneous if all of its terms have the same total degree. And recognizing these types isn't just about putting labels on things, it tells us exactly which tool from our toolkit we need to grab to solve it. That's a great question, right? They pop up in nature all the time, but we can also build them ourselves, from scratch. We can actually take a description for an entire family of curves, say all circles that are centered at the origin, and figure out the one single differential equation that governs every single one of them. And there's actually a recipe for it. First, you just write the general equation for the family, and it's going to have some arbitrary constants, like an a or a b. The number of those constants tells you exactly how many times you need to differentiate the equation. Then, after you've done the derivatives, you just use some good old algebra to get rid of all those constants. And what you have left, that's the pure fundamental differential equation for that entire family of curves.
So we can identify them, we can classify them, we can even create them. But the whole point, the ultimate goal, is to translate them back, to turn one of these complex equations about change into a familiar function that we can actually work with. That's what we mean when we say we solve it.
And when we do solve them, we usually find two kinds of answers. First, there's the general solution. You can think of this as the master blueprint. It still has those arbitrary constants, and it describes the entire family of possible curves. But if we have some starting information, like we know exactly where an object began its journey, we can nail down those constants and find a particular solution. And that's not the blueprint anymore. That's one specific, actual building constructed from it.
To find these solutions, mathematicians have built up an incredible toolkit over the years, with a specialized tool for pretty much every type of equation you can imagine. So let's take a quick look at some of the most common ones.
The very first tool you almost always reach for is called variable separable, and the name really says it all. If you can use algebra to just shuffle everything around and get all the y stuff on one side and all the x stuff on the other, you're golden. Just integrate both sides and boom, you've got your solution.
Now, for linear equations, we have a real powerhouse of a tool. We calculate this special thing called an integrating factor. It sounds complicated,
But when you multiply the entire equation by this factor, it performs this amazing trick. It magically transforms one side into a form that's super easy to integrate. It's a really elegant move that just cracks these problems wide open.
And remember those homogeneous equations we identified earlier? Yep, there's a tool for them too. By making a really smart substitution, specifically you let y equal v times x, the entire equation just transforms. It morphs from a tricky homogeneous problem into a simple variable separable one, which, hey, we already know how to solve.
Okay, so we've learned some grammar, we've looked at the basic translation techniques. But why? Why learn this whole complex new language in the first place? Well, the answer is pretty simple actually, because it's the language that the world around us is written in.
I mean, just look at geometry for a perfect example. Differential equations can define the properties of any curve at any single point. We can use them to find the precise slope of a tangent line, or even to discover a whole new family of curves that intersects another family at perfect right angles. They are the engine that powers analytical geometry.
But it goes so much further than that. As the mathematician Stephen Strawgast famously said, they are the language in which the laws of nature are expressed. Think about it. Newton's laws of motion, Maxwell's equations for electromagnetism, how financial markets behave, how diseases spread, the most fundamental rules that govern our universe are all written as differential equations.
So here's the crucial thing to take away from all this. Differential equations aren't just some abstract math concept. They are a lens for seeing the world. So the next time you see something changing, anything at all, ask yourself, what's its rate of change? And what does that rate depend on? Just by asking that question, you're already taking the first step to thinking in, and maybe even one day writing, the language of change yourself.